tardes a todos. Es un honor poder ser coorganizador de esta sesión junto a Juan Carlos Pozo. Muchas gracias por participar. Y bueno, esta sesión es de todos, así que bienvenido a todos a nuestra sesión. Para comenzar con nuestra sesión de análisis de ecuaciones en derivadas diferenciales, tenemos al profesor Nikola Kamburov de la Pontificia Universidad Católica de Chile y nos va a conversar sobre Non-Trivial Solution to Serif Problem in Angular Domain. Muchas gracias, Nicolás.
Gracias.
Bienvenido.
Muchas gracias. Primero quiero agradecer a Juan Carlos y a Leonelo por organizar este evento, por reunir a todos nosotros como comunidad en estos tiempos difíciles en el país y en el mundo. Bueno, y ahora si me permiten, voy a dar la charla en inglés. I will talk about a very classical topic, which is Sterin's overdetermined problem, elliptic problem. This is joint work with my former master student, Luciano Sharafia, who is now a doctoral student at the University of Pisa in Italy. Okay, so let me tell you or remind you, if you have seen this, what the Sterin overdetermined problem is about. It involves a elliptic, let's say a Poisson equation with a right-hand side, which could be a Lipschitz nonlinearity. It could be more complicated. It could depend on the gradient too, but in this case, I'm going to consider just a semi-linear problem, and in which we're looking for positive solutions in a domain in the Euclidean space, and we specify not just Dirichlet data, constant Dirichlet data on the boundary, but also constant Neumann data on the boundary. So in this sense, the problem becomes overdetermined. And by the way, this is just something of convention here. By U, I'm gonna denote the inner normal derivative at the boundary. Okay. So the act of specifying both Dirichlet and Neumann data at the same time has a very strong effect of rigidity on the domain. Only a handful of shapes omega can admit solutions to this problem. And the subject started with Sterin's classical paper from 1971, in which he proved that indeed, if the domain that we are considering is bounded, then it's gotta be a ball as symmetric as possible. And the solution, U, has to be radially symmetric. The method of proof is extremely elegant. It's the moving plane method, and this is the first instance of the moving plane method in the PD literature, which Sterin adapted from previously. It was used by Alexandrov in the context of constant mean curvature surfaces. And the basic idea, I'm not going to go into the details of the method, is the following: that you take a plane that very, very far away from the domain with a normal in an arbitrary direction. Let's say in this case the normal is along x1, the axis x1, and you start moving it towards the domain. At some point, it's going to start intersecting the domain omega, and what you do is that the cap, which is the intersection of the plane and the domain, you reflect it across the plane, and there you define a function w, which is the difference between solution u and the solution u at the reflected point across the plane. Okay, and now what you do is you are I call it, you're riding the wave of the maximum principle. So the maximum principle tells you initially this W is going to be positive, and this allows you to further push this plane, and you can do this up until a certain moment, not forever. Either this reflected cap here becomes internally tangent to the domain. This is one possibility. Or the other possibility is that the plane P becomes orthogonal to the boundary. Okay, in either case, what happens is that, by a very quick argument using the Hopf maximum principle, the function W needs to be exactly equal to 0. This is the consequence of the constant Neumann condition. Yeah, and therefore, the solution U is symmetric across, reflection symmetric across the plane P. And well, if you know it's reflection symmetric across any plane, it's reflection symmetric. It has to be radially symmetric. Okay, but so here is an interesting feature of the method, is that this symmetry comes at the same time as establishing the monotonicity of the solution. It's precisely because this W, the difference here, is positive while you can run the method, and therefore the normal derivative along the plane B has to be negative. And what you get is a radially symmetric and monotonically decreasing solution. Okay, so yeah, the next very natural extension to this problem is to domains with holes. So here you consider a domain whose boundary has different connected components, and you specify again constant Dirichlet and constant Neumann data on the boundary components, but here you allow these constants to be distinct from boundary component to boundary component. Okay, and so yeah, you can ask the question: is the shape rigid in this case? And a theorem by Reichel, which was extended by Sirakov, says under certain conditions this is what happens. Indeed, that if the inner slopes that you specify on the inner boundary component, if the inner slopes on the inner boundary components are non-positive, then omega has to be necessarily just the annulus. Actually, you can have only one interior boundary component, gamma 1. The domain is the standard annulus, and the solution is again radially symmetric. So yeah, the way that it's proved is again uses the moving plane method in a very clever just modification, where you have to take care of just the details of reflecting these exterior domains here, domains with holes. Okay, so this is all good, but what happens if we drop the assumption of the non-positiveness of these inner slopes, right? And the inner slope is non-positive. Does rigidity still hold in this case? And this is the problem that we set out to study with my students. And the first thing that one sees is that one can very easily cook up, PDEs, the Poisson type, where the solutions are defined on a standard annulus, but radial, but have this profile. They're non-monotone. Okay. So if you hope to prove rigidity in this case, then you cannot do it with the moving plane method, because the moving plane method will produce strictly monotone solution, and you have solutions with non-monotone profiles. Yeah, and well, what we discovered is essentially that actually the radial symmetry can be broken. And this is our main result, that there exists real analytic annular domains, which are not the standard annuli, where you can solve the Poisson equation with a constant right-hand side, zero boundary condition on the outer component, constant, positive constant on the inner component, and the same constant inner slope on both boundary components. Okay. And there is we found a very neat connection afterwards to the so-called Cheeger problem, which is a problem in shape optimization, in which you take a bounded domain and you want to study this number, this infimum, which is known as the Cheeger constant, which is, what you do is you consider subsets of omega, and for these subsets, you consider the ratio of the perimeter over the volume. If this infimum is realized for a certain subset, the subset is called a Cheeger set. And there is a nice situation when this Cheeger set is exactly the domain omega. And in this case, omega is called self-Cheeger. Well, turns out that the domains that we construct in this theorem are self-Cheeger, and they're examples of non-radially symmetric self-Cheeger sets. And the proof is very easy. It's an application of the divergence theorem, coupled with the fact that a solution U that has constant Neumann data, constant positive Neumann data, inside will have a gradient which is strictly less than this constancy. Okay. All right. Well, the construction of such non-trivial solutions to overdetermined elliptic problems has been prominent in the last decade, and most of the work has been done in relation to a conjecture of celebrated conjecture of Beresticki, Caffarelli, and Nirenberg. Conjecture says the following: that if you say omega is an unbounded smooth domain and has a complement which is connected, then if you consider the original overdetermined problem, the Serrin overdetermined problem, constant Neumann condition and constant zero boundary condition on every boundary component, if this original problems admits the solution, then the possibilities for omega are just these here. Either omega is a half space, it's a complement of a ball, or it's a cylinder, or it's each of these, crossed with the Euclidean space. You can very easily construct once you have a domain which solves the overdetermined problem. Then you cross it and extend the solution then constantly in those directions. Well, it turns out that this conjecture is false, and work of Sigbaldi, Pier Alberto Sigbaldi, the University of Granada, and collaborators, they constructed counterexamples in all dimensions. So in 3 dimension, one can construct a counterexample using the right-hand side lambda u. So you have an eigenvalue problem, and the domain omega is a perturbation of a cylinder. Okay, and the counterexamples arise for very particular values of lambda. And well, this works only in 3 dimensions and higher, because in 2 dimensions the complement of a cylinder is not connected. Okay, so then the counterexample, family of counterexamples that works in all dimensions is the one below that they constructed later, which is a perturbation of the complement of a ball. And again, this time for a different nonlinearity, Lane-Hamden nonlinearity in the subcritical regime. Yeah? And again, they arise for appropriate values of lambda. And I say arise, but the proper word here is they bifurcate from these trivial, in some sense, solutions at critical values of this lambda, which is treated as a bifurcation parameter. So the method of proof is the bifurcation method. It's the one that we also use in our work. And I will explain it in the context of our work. There we go. So how to phrase the overdetermined problem as a bifurcation problem. So in our case, the right-hand side is just a constant one. And we take the standard annulus of inner radius lambda, outer radius 1. And we consider the solution to the equation Laplace u equals negative Laplace equals 1, which has 0 boundary condition on the outer sphere, the sphere of radius 1, and satisfies constant Neumann condition, and this is a positive constant, on both boundary components. And there is just one function that satisfies this boundary condition. And this is going to be the trivial branch of solutions, which we are now going to perturb. Okay, so we take the standard annulus, which admits this radial solution, and we deform it. And the deformations are just a pair of functions in which we deform the inner components in the inner normal direction and the outer component also in the inner normal direction. So that's why there's a plus and a minus sign here. So this is the deformation. Now we solve the Dirichlet problem in this deformed annulus with this with the 0 Dirichlet data on the outside and a lambda, the same a lambda, which is the constant for this trivial solution on the inner component. Okay, and we define the following operator, which measures how far away is going to be the inner normal derivative from the C lambda. Okay, so and this is just a normal, a nice, convenient normalizing factor. So then, obviously, the solution U of this Dirichlet problem will solve the overdetermined problem if this operator is 0 on certain deformation. Okay, and we have, of course, the fact that we have the trivial branch of solutions. So when we don't deform, we still get 0 for every lambda. So now that the goal is to find a non-trivial branch of solutions which grows out of this trivial branch for certain values of the bifurcation parameter. And the device, well, that is we are going to use then to construct this non-trivial branch is the Crandall-Rabinowitz bifurcation theorem. So in the Crandall-Rabinowitz bifurcation theorem, you have a smooth family of operators, jointly smooth actually, the bifurcation variable as well as in the variable that ranges over the Banach space, and it's in the neighborhood of the Banach space, neighborhood of 0, and you have the trivial branch of solutions. So the operator is equal to 0, 0 for all lambda, and for certain critical lambda 0, where the linearized operator is singular, is exactly the location where we expect the bifurcation to occur. Okay, but in this setting of the Crandall-Rabinowitz theorem, what you want is that the linearized operator is a Fredholm operator with one-dimensional kernel, one dimension, and again, enclosed image of codimension 1. And the third condition, which is an important technical condition, is this one, which I'm not even going to enunciate, but it's a, yeah, one can think of it as a condition of transversality. So if this is met, then indeed there is at this lambda 0 a curve, a branch of solution, which is different from the trivial branch. Okay. So of course, then the object of study is the linearized operator and understanding at what point it becomes singular. Well, that problem, when the linearized operator becomes singular, it can be phrased more broadly as an eigenvalue problem, and trying to understand for what value. Well, first of all, how the eigenvalues vary with lambda, and when do the eigenvalues cross 0. And the crossing of 0 has to be also done in the way that this transversality condition is going to be satisfied. Okay. One computes the linearized operator for the operator f, and it's an operator of Steklov type, where each component involves the Dirichlet-Neumann operator. So here phi is the harmonic function with boundary values given by the function by the functions v, which provide the deformation. Okay, well, yeah. So this is a very nice operator. It's formally self-adjoint. So even though initially it's an operator on C2 alpha. I forgot to mention that these are the deformations that we take, the space of deformations. And this is a useful function space because of elliptic regularity theory. But yeah, if you can now lift this operator to an appropriate L2 based Hilbert space and study the eigenvalues there. So it's formally self-adjoint, and it is if you just do separation of variables, it is invariant on the direct sum of the subspace of the spherical harmonics of degree k. So each subspace corresponds to each of the two boundary components. Okay. So now, so in order to study spectrum of this operator, you just have to study its action on the subspace. But its action on the subspace, appropriate basis, orthonormal basis, just understanding the eigenvalues of a 2x2 matrix, which is symmetric matrix. There are two real distinct eigenvalues. And I did not mention this before, but we have a very explicit. The right hand side, the constant right hand sides of the Poisson equation is so simple that you can write explicit formulas. This is sometimes a blessing. It could also be a curse, and because when you have formulas that are explicit, sometimes you don't see what's going on. And indeed, the formulas that one gets for the eigenvalues are very, very complicated. Okay. So understanding how the eigenvalues, these two eigenvalue branches, vary with lambda was the hard part of our paper. And, so this is what we found, and this is the main technical result. We found that for the eigenvalue branches for k equals 0, for the degree 0, that correspond to the degree 0 spherical harmonics, both these eigenvalues are negative for all lambda. Now, if you look the eigenvalues corresponding to the first spherical, degree 1 spherical harmonic, well, the first one is negative, and the second one is 0. Okay, so and for every lambda, it's 0. And this is fine. This is good. This is because this kernel is this always present kernel is the one due to the translations of the annulus, of the standard annulus. Okay, so you expect it to be there. And then for k greater than or equal to 2 and fixed lambda, the eigenvalues increase in k. Okay, so this means in particular that the second branch of eigenvalues will no longer, after case 2, 3, etc., will never contribute to the kernel of the operator. Okay, so any kernel would come, well, besides this constantly present component, any component of the kernel would come from the first eigenvalue branch. And we show that the first eigenvalue branch is strictly decreasing in lambda and changes sign at a unique bifurcation value lambda k. And these eigenvalues are differentiable, well, they're smooth functions of lambda, and well, the derivative is strictly negative. So this condition here is precisely what gives us the transversality condition in the kernel-Rabinowitz theorem. And well, if you want, one considers all these bifurcation values to lambda k, which k then form an increasing sequence that approaches 1. So you will have just a sequence of bifurcating domains that are bifurcating for thinner and thinner angular domains. Okay, so remember, in order to use the kernel-Rabinowitz theorem, I need a kernel of dimension 1. Okay, whereas I have a constantly present kernel here, which has multiplicity, and also I have, for each critical value lambda k, the degree k harmonics also, the dimension of that subspace is bigger than 1. So how do you deal with this? It's a bit cheating. No, not cheating. It's the proper way to do it. You simply work in gene-variant function spaces for an appropriate subgroup of the orthogonal group. And that way you simply eliminate the multiplicity of the kernel. So you want a particular group G that satisfies these two properties, that indeed there is a unique gene-variant spherical harmonic for each of the admissible degrees, because you're going to kill some degrees of spherical harmonics. Some will remain, and those that remain, you want them to be one-dimensional. And you also want that this symmetry group to be such that well, you want to kill all deformations that will produce just a congruent annulus. So we don't want a deformation that produces a translation or a dilation, right? You want a truly distinct annular domain, different from the standard day. And it's not very hard to see that there are such groups that do it. Also, by the way, the fact that you impose this condition here, it implies that that way you can kill off these the degree 1 spherical harmonics, which are responsible for translation. So that constantly present kernel is gone from the picture. Yeah. So that's how you do it, and I think I'm out of time. And let me end just with the diagram how these things behave. Yeah, thank you very much.
Muchas gracias, Nicolás. Agradecemos, Nicolás, por su muy buena presentación. Muchas gracias, virtuales.
Gracias.
Preguntas, comentarios.
Tengo un comentario.
Sí.
In the beginning, you were saying that this has some applications can be applied to some shape optimization kind of problems. So I think there was one conjecture, and I think one of the references which you mentioned, when the constants are negative, when you have a decreasing derivative, you said in the beginning that it's known that this has to be an annular domain.
Yeah.
These counterexamples are when some of them are positive, no?
Exactly. So this is what we studied. So if one of these inner slopes is actually positive, so that way,
and there is one problem. I think it's an eigenvalue optimization problem. So if you take a 2D domain, then so what is the among domains with a hole? What is a like, I mean, of given volume? Okay. Which is the one which has the maximum or the minimum first eigenvalue?
Indeed. Yes. Yeah. No,
I think you can solve it with this. I mean, from what you said in the literature, of course, it's probably not so relevant to your talk, but it just came to my mind.
No, so. Yeah, Thank you for I know of this as well, but I didn't have time to put it in the slide. But yeah, it's a very neat connection as well to that particular that problem which arises from optimization of the first eigenvalue.
¿Más preguntas o comentarios?
Sorry, your talk was very interesting, and I would like, I mean, I think I could get the paper, so maybe I will contact you and have.
Oh, wonderful. Yeah. We should talk, definitely. All right. Yeah, let me clear the screen.
Ok, no hay más comentarios.